G'day YouTube, Warbles on a lot here. Today we're going to look at carbon capture and storage. And we're going to ask ourselves, is carbon capture and storage thermodynamically impossible? It's a curious question, isn't it? Because there's an awful lot involved. And because we're talking about coal, and coal is a really old power source, we're going to have to use the British thermal unit. So welcome to the British thermal unit. It's the amount of energy required to raise the temperature of 1 pound or 453 grams of water by 1 degree Fahrenheit or 0.55 of a degree Celsius. Just for curiosity's sake, it's also the same amount of energy it would take to raise that single pound of water, or feathers or anything else, 768 feet vertically up into the sky, aka 234.08 metres. Next thing we've got to consider is the energy density of various fuels. Now, wood has 6,000 to 8,000 BTU per pound. Hard coal, anthracite, 13,000 to 14,500 BTU per pound. Soft coal, bituminous, 12,000 to 14,500 BTU per pound. And fuel oil has 20,000 to 22,000 BTU per pound. Okay, so what's in this stuff? Wood, 50% carbon, 40% oxygen, quote, some hydrogen, no sulfur, 8% moisture. Hard coal, 91.5% carbon, 3.45% hydrogen, 4.16% ash, 1.34% moisture. Soft coal, bituminous, 75.02% carbon, 20.34% hydrogen, 3.47% ash, 0.56% sulfur, 0.61% moisture. Fuel oils, 86% carbon, 1% oxygen, 13% hydrogen. Anytime you hear anybody talking about clean coals, there are two things they're talking about. One of them is this ash content. If they pulverise the coal and wash the coal, they hope to float the ash out of the coal so that they don't have to filter the gases and trap the ash. That's what they're talking about that away. Still on the subject of clean coal, I'm sure you know that to get the energy out of the coal, you have to combust it. You have to oxidise it. You have to burn it in the air. Now, to combust the coal, as I was saying, to combust 1 pound of coal, or 453 grams, requires, in theory, 12 pounds, or 5.443 kilograms of air, i.e. 150 cubic feet, or 4.247 cubic metres. However, that's theoretical. In practice, it takes 20 to 24 pounds of air, or 9.072 kilograms, to 10.886 kilograms, i.e. 225 to 300 cubic feet, or 6.371 to 8.495 cubic metres. And another way they talk to you about clean coal is that they talk about high temperature supercritical combustion boilers, in which case they try to get from the practical 225 to 300 cubic feet of air per pound of coal down to the 150 cubic feet of air per pound, and they do that by pushing the combustion temperature in the boiler up, and the limit is the steels or the metals in the boiler pipes. So that's clean coal pretty much dealt with. The simple fact that there's between 75% and 91% carbon in the coal means that you're going to make a huge amount of carbon dioxide when you burn it. Now, whereas you can burn LP gas and run the hot gas in a turbine to convert the gas energy into, or gas heat energy, directly into rotational torque, you can't do that with coal because the ash content we talked about earlier will literally sand the blades away. So you have to do something else with the energy that comes off the burning coal. What they do is they burn the coal under a boiler. Now, this kind of boiler is what's called a water tube boiler. And the way it works is that this tank up the top here is full of water. The water comes down into a gallery gets fed into a series of parallel pipes that run up over the firebox. Here's your coal burning in the grate. The fumes from the burning coal, the hot gases, come up running around these water pipes along the bottom of the boiler, down past this baffle wall, down around these water pipes, up past these, and to the flue out here. So you get sort of 3 goes at the hot fire, and you got a lot of surface area of metal exposed to the fire on one side and the water on the other side. So a horizontal water tube boiler is about as good as they get, as compared to a vertical fire tube boiler, in which the tubes run through the centre of the boiler from the firebox to the flue, or a horizontal fire tube boiler, in which the fire comes up here and runs through tubes in the boiler. Once again, we've got to resort to archaic terms. Because the first steam engines were sold to people who ran coal mines, the steam engine was replacing pit ponies and draft horses. So the definition of a horsepower is the amount of energy it takes to raise 550 pounds lifted 1 foot in 1 second, i.e. 550 foot-pound seconds. The way it was calculated was they had one horse, an actual horse, walking on flat ground, pulling a 1-inch diameter hemp rope over a 1 foot diameter steel pulley wheel, going down a vertical shaft where there was a wooden bucket that weighed 50 pounds empty, containing 50 gallons of water, and an imperial gallon weighs 10 pounds. So therefore 550 pounds of water plus bucket raised vertically 1 foot in 1 second, that's 1 horsepower. Once you start getting into rotary steam engines rather than oscillating beam engines, your rotary steam engines start measuring torque, which is what happens if the steam engine turns the pulley and the rope gets wrapped around the pulley a couple of times, and you measure the twistiness in the shaft. Right, back to boilers. To have a boiler generate enough steam to run it through an engine and generate horsepower, 10 to 16 square foot of boiler area per horsepower, that's 0.929 to 1.486 square metres per 736 to 742 watts, i.e. 1.255 to 2.008 square metres of boiler area per 1,000 watts or kilowatt. And as I said, it's the horizontal water tube boiler which is the most efficient. That's your sort of 10 square feet to the horsepower. If we run the steam that comes out of the boiler into a turbine, then we can use the torque produced by the turbine to turn a generator or an alternator. And then we can use the waste steam to go into a condensing tower, turn it back into water, and run that back to a boiler pump, which will put the cold water back into the boiler. So you don't even actually waste any water. Isn't that clever? Now, they didn't go straight to steam turbines. They initially used reciprocating steam engines. Now, this one's a single action steam engine. Here's another one, which has a steam turbine or a reciprocating steam engine. This set of plans gives you enough information to build one. It even has a sliding valve steam chest, which operates thusly on the eccentric principle of the crankshaft. In this sort of device, steam comes in, it pushes the piston down, the connecting rod turns the crankshaft, the residual inertia in the flywheel then pushes the piston back up, exhausts the steam, and the cycle repeats. Single action steam engine. That's about 10% efficient at turning the energy in steam into rotary torque. If we come up to a double action steam engine, steam pushes the piston down, exhausting out here. Steam pushes the piston up, exhausting out there. So the piston is driven both ways. Okay, maybe 20% efficient at getting the energy out of the steam and turning it into torque. The next idea was the double action multiple expansion steam engine. So your steam comes in here, and while it's pushing the piston down, the old steam is exhausting out to here. And it's pushing this piston up, and the old steam is exhausting out to here, and it's pushing this piston up. And the pistons and the cylinders get larger as the steam expands. So you can get the very, very most out of really, really high pressure steam. Now, the thing is, this can get maybe 35% of the heat energy out of the steam and turn it into rotary torque in a single shaft. But the boiler can only get 50% of the energy that's in the flue gases and put that into the water. So you've got 50% of 35%. So the most efficient steam engine, mechanical, reciprocating, piston type steam engine, was only 17.5% overall efficient. And that's not good. You know, like my car engine's 25% or so. Therefore, they got rid of all that reciprocating machinery and they moved to blowing steam on aerofoils on a flywheel. And they didn't just stop at one single row of blades. And as the steam expanded, the space it expanded into got bigger and bigger and bigger. Until by about 1885, when this book was published, steam turbines were 95% efficient at getting the energy out of the steam and into the shaft by using multiple rows of stators and rotors to squeeze all of the energy out of the steam. Okay, so when you hear somebody from the coal industry or a right-wing politician say that the way to the future is clear, we're going to keep burning coal because we are going to develop carbon capture and storage technology, what they mean is we're going to suck up the entire flue emissions. We're going to pump the flue emissions into lime water because that will absorb the carbon dioxide. Then there's going to be a mystery box full of technology that we don't talk about. Then we're going to put the liquid carbon dioxide into a refrigerated electric powered tanker truck, and we're going to carry it some indeterminate distance to where there is a disused mine shaft in a stable geological formation. And we're going to pressure inject the liquid carbon dioxide down into the old disused mine. And the reason we're expected to believe this is because somewhere in the world somebody has done this. In a laboratory, on a bench, they've burnt some coal. They've used electric power to blow the coal fumes into their lime water. They've probably done that through several flasks. Then they've taken their lime water and they have evaporated all of the water away from the lime and carbon dioxide. They've then put their carbonated lime, solid, into an oven. They have heated it and driven off the gaseous carbon dioxide, which then goes into a 3-stage compressor, powered by a motor. Then they refrigerate it, right? Because dry ice boils at minus 70 degrees Celsius, and liquid carbon dioxide takes about 1,000 psi to organise. And all of these processes are all powered by a coal-fired power station somewhere else, shitting into the sky. Nobody has ever explained how you do all of this powered by the energy coming out of the coal that you are actually burning and attempting to scrub. Here's how it looks. Pound of coal, 14,500 BTU. Boiler efficiency 50% leaves you with 7,250. Turbine efficiency of 95%, leaving 6,887.5 BTU. Alternator efficiency of 85% leaves you with 5,854.375. Motor efficiency of 85% leaves 4,976.2187. Fan efficiency of 85% leaves 4,229.7858 BTU. Let's say the decanting and the evaporation is run by siphon and solar power, so that costs you nothing. Oven efficiency, 95% leaves you with 3,806.8072 BTU. Motor efficiency, 85%, leaves you with 3,235.7861 BTU. Compressor efficiency, 25%, goes you down to 808. Refrigerator motor efficiency 85% leaves you with 687.6. Refrigerator compressor efficiency 25% leaves you with 171.9. So you're going to use 98.814% of the energy in the coal just to turn the gas into a liquid. With 1.185% of the energy that was in the coal to run your electric powered refrigerated tanker truck, take it to the coal mine and put it back down underground. And I'm sorry, but I'm pretty sure that means impossible. Ciao.